Before I started my talk, I would like to thank the organizers for the opportunity to present some results on this conference, and for the possibility to see and listen to interesting talk of researchers from different countries. Also, it should be noted that this conference was very good organized, and so thank you very much to the organizer for this. So let me start my talk. It is an interesting problem to study the asymptotic behavior of eigenvalues and eigenfunctions of spectral problems in perceived domain, since different unexpected phenomena appear in the asymptotic behavior of the spectrum. In addition, such problems have various important implications. In my talk, I'll explain what thick junctions are, and then present small review on spectral problem in thick junctions, and then present my results. So, thick junctions of type KPD is the union of some domain, which is called the junctions body, and a large number of thin domain situated epsilon periodically along some manifolds on the boundary of the junctions body. This manifold is called the join zone. The thin domains in thick junctions can have variable thickness and even non-Lipschitz boundaries. The small parameter epsilon characterizes the distance between neighboring thin domains and their thickness. And the smaller epsilon, the more attached thin domains there are in a thick junctions. The junctions body and the join zone can also depend on the parameter epsilon. The type KPD of thick junctions refers respectively to the limiting dimensions of the junctions body, the join zone, and each of the attached thin domain as epsilon tends to 0. For example, on this picture, you can see thick junctions of the type 3, 1, and 1. It should be noted that the type of a thick junction in some cases significantly change the asymptotics. These classifications was given in my joint article with Sergei Nazarov, where different boundary value problems and spectral problems were investigated. And the aim is to study the asymptotic behavior of solutions to boundary value problems in such thick junctions as epsilon tends to 0, that is, when the number of the attached thin domains of thick junctions infinitely increases and their thickness vanishes. Thick junctions are a prototype of widely used modern engineering constructions, as well as many other physical and biological systems. On the next slide, you can see some examples of such a system shaped like a thick junction. Therefore, the study of properties of solutions to boundary value problems in such domain attracts many mathematicians. An extensive review of results obtained in this area is presented in my joint monograph with my former postgraduate students, published last year. Here, I would like to mention names of some mathematicians who intensively studied and study such problems, and note that the first paper in these directions were papers by Hruslov, where the asymptotic behavior of the green functions for the Helmholtz equations in unbounded thick junctions was studied. I will show you some picture made from these papers. And this work by Hruslov and Igorova, asymptotic behavior of solutions of the second boundary value problems in domain with random thin channels. You see here the picture below, was translated in English. So now return to spectral problems. The first asymptotic results for spectral problems were obtained in my joint paper with Sergei Nazarov in 1993, where we study the asymptotic behavior of eigenvalues and eigenfunctions of the Neumann Laplacian in thick plane junctions of the type 2, 1, 1. For these thick junctions, you see the junction's body omega 0, and the join zone is the interval 0a, and the thin rods filled out the rectangle D in the limit passage as epsilon tends to 0. For fixed value of epsilon, there is a sequence of eigenvalues with the classical conventions of repeated eigenvalues, and corresponding eigenfunctions can be orthonormalized by the following way in the space L2 of omega epsilons. Here, delta sub nm is the Kronecker symbol. So the aim was to develop a rigorous method to study the asymptotic behavior of eigenvalues and eigenfunctions as epsilon tends to 0, that is when the number of the attached thin rods infinitely increases and their thickness vanishes. It should be noted that the study of perturbed spectral problems is more complicated than the study, for example, the asymptotic behavior of solutions to boundary value problems. Since for spectral problems, we have a countable set of solutions, both for the initial problems and for the corresponding limit problems. For these problems, the homogenized problems is as follows. We have the same relations in the junctions body as in the initial problems. And in the rectangle D, we have ordinary differential equations with respect to x2 and with Neumann conditions on the lower base of the rectangle D. And the following transmission conditions in the join zone. Here, the letter L denotes the length of the thin rods, and H denotes their relative thickness. I wrote them in different colors to see their influence on asymptotics. The homogenized problems is reduced to the nonlinear spectral problems for the operator functions L in the Sobolev space H1 of omega 0. And here the operator A1 and A2 are self-adjoint compact operator in this Sobolev space defined with the following formulas. Theorem on existence and concentrations of the spectrum for such operator functions and minimax principles for eigenvalues were proved in the following my papers. And from results obtained in these papers, it follows that the spectrum of the operator functions L contains normal eigenvalues, and also the left accumulation points P sub m that divided the eigenvalues into non-decreasing sequences. So we have the following structure of the homogenized spectral problem. The most remarkable things in the spectrum structure of the homogenized problems is the presence of gaps to the right of the points PM, here and here. And for the first time, such a structure of the spectrum was discovered in our paper with Sergei Nazarov. In some cases, these red points of the essential spectrum can become the segments. This happens when the thin rods smoothly change their length. In 2001, I studied a spectral problem in a thick junctions with the smooth variable length of the thin rods. The length of the thin rods is described with the smooth functions L. In this case, the thin rods filled up the domain d sub L of x1 in the limit passage as epsilon tends to 0. And the spectrum of the homogenized problem consists of finite number of the closed interval of the essential spectrum, red ones, and finite number of non-decreasing sequences of eigenvalues between them. In addition, we can control the number of these intervals and their lengths with the help of functions L. For example, if the minimum of the functions L is equal to 0, then the structure of the spectrum is as follows. It turned out that the asymptotic behavior of the spectrum is highly sensitive to boundary conditions given on the lateral boundaries of the thin domains. The asymptotic estimates for eigenvalues and eigenfunctions of spectral problems with different boundary conditions, Neumann, Dirichlet, Robin, Stiklov, in 6 junctions of different types were proved in the following my papers. A natural question arises: what happens when the function describing the length of the thin rods is not smooth? I have considered some examples of such thick junctions and called them thick multi-level junctions. A thick multi-level junctions is a thick junctions in which the joint thin domain are divided into finite levels depending on their geometrical configuration. Besides, the thin domains from different levels are epsilon periodically alternated along the joint zone. So for this thick multi-level junctions in this picture, the functions describing the length of thin cylinders is an epsilon periodic step function. I considered various Robin conditions on the lateral surfaces of thin cylinders. As a result, the corresponding homogenized spectral problems is reduced to the spectral problems for the operator functions L. And here, the coefficients k sub I here and here appeared from the boundary Robin conditions. Many new phenomena in the asymptotic behavior of the eigenvalues and eigenfunctions of spectral problems in thick cascade junctions with concentrated masses were discovered in our joint paper with Gregory Chechkin. Asymptotic cascade junctions is a thick multi-level junctions in which the thin rods from the first level vanish as epsilon tends to 0. Here I will only mention the fact that we have discovered a new type of the skin effect, which we called the spatial skin effect. This effect means that there are vibrations in which the thin rod from the second levels repeat vibrations mode of the joint zone. So now let us consider thick junctions with a branch fractal structure. I started studying boundary value problems in thick junctions with a branched fractal structure in 2015, and the first results were obtained for perturbed semi-linear parabolic problems with non-linear perturbed Robin conditions. Today, I will show you results for spectral problems in such thick junctions. So, a model of thick junctions with a branch fractal structure consists of the junction's body omega 0. The interval 0a is a joint zone. Let us take a large integer n and divide it, the interval 0a, into n equal intervals of the length epsilon, that is equal a over n. To the middle of each this interval, we attach thin rectangle of the length L1 and width epsilon multiplied by h sub 0. The union of this rectangle is called the zero layer and denoted by g sub epsilon 0. And obviously that in the limit, these rods filled out the rectangle D0. Then to the lower basis of these thin rods from 0 layer, we join thin rods from two different classes, G sub epsilon 1, 1, blue set, and G sub epsilon 1, 2, green set. The length of these thin rods is equal L2, but the width is different and it is equal to epsilon multiplied by H11 for the rods from the first class and epsilon multiplied by H12 for the other one. In the limit, the thin rods from each class filled out the rectangle D1. Then, by the same way, we join thin rods from four different classes: red, yellow, pink, and gray. And the union of these rods is called the second branching layer. So, on this slide, you can see the mathematical description of our thick fractal junctions omega sub epsilons. Here I would like to pay your attention on the blue constant, H sub 0, H sub 1m, and H sub 2m. They are relative thickness of thin rods from different classes. I've written these letters in color to observe their influence on the asymptotic. Thus, our thick fractal junctions consist of junctions body, omega 0, and a large number of thin fractal roots or thin fractal branches that are epsilon periodically situated along the join zone, the interval 0, A. A thin fractal root can have finite number of branching layers. In our case, for these junctions, we have two branching layers, this one and the second one. This is the model of thick fractal junctions. I am considered it only to simplify formulas and calculations. However, all results without significant changes are transferred to spectral problems in thick fractal junctions of more complex branched structure. For example, the branch zone can contain nodes of different shapes. On next slide, you can see some examples of real systems shaped like thick fractal junctions. Here you see an industrial constructions whose fractal rods have four branching layers. This one, second, the third, and the fourth. So now return to our spectral problem. So in omega sub epsilons, we consider spectral problems for Laplacian with perturbed Robin boundary conditions on the vertical sides of the thin fractal roots. Here the index I correspond to a branching layer and the index M correspond to a class from the ith layer. Also in the Robin conditions, you can see the intensity factors epsilon to the power alpha sub I, where these parameters are greater or equals 1. It is possible to consider the case when some parameter alpha sub I less than 1. And if I have time, I will make a remark at the end of my talk. On this vertical sides, we have periodical conditions. Also, we have Dirichlet conditions on some curve on the junctions body, and on the other part of the boundary of the thick fractal junctions, we have the uniform Neumann boundary conditions. For these problems, we introduce the corresponding Hilbert space, capital H sub epsilons, and with the following scalar product. And it is easy to verify that the spectral problems, our spectral problems, which I called CP epsilon, is equivalent to the spectral problems for self-adjoint positive compact operator acting in this Hilbert space. So for each fixed value of epsilons, all eigenvalues of problem CP epsilons can be ordered as follows, and the corresponding eigenfunctions can be orthonormalized in the space L2 of omega epsilons. Recall here delta sub nm is a Kronecker symbol. The aim is to study the asymptotic behavior of the eigenvalues and eigenfunctions as epsilon tends to 0, where that is when the number of the attached thin fractal rules infinitely increases and their thickness vanishes. In particular, we should find the corresponding homogenized spectral problems, determine its spectrum, study the asymptotic behavior and prove the asymptotic estimates for the eigenvalues and eigenfunctions, and of course, study the influence of the parameter epsilon sub I on the asymptotic. Taking into account the Dirichlet conditions, it is easy to prove the inequalities too for the eigenvalues, and by virtue of the minimax principle for eigenvalues, it is possible to prove the inequality 3. Based on these estimates, we seek the leading term for of the asymptotics for an eigenvalues lambda sub n of epsilons here, and after the index n is omitted in the form 4. The asymptotic ansatz for the corresponding eigenfunctions in the junctions body has the form 5, and in each thin rows has the form 6. I call these ansatzes outer expansions. Then we use the asymptotic expansion technique of multi-scale analysis. We put these ansatzes in our problems, collect coefficients at the same power epsilons. If needed, we use Taylor series and derive relations for the leading term of these ansatzes. Unfortunately, I have not so much time, so if I have time at the end of my talk, I will show it in details. And now I will show you only these relations. Obviously, that for the first term of the ansatz 5, the functions v0 plus, we obtain the same relations in the junctions body as in the initial spectral problems. But for the leading terms of the ansatz 6, we obtain different relations. So for in the rectangle D0, we get the ordinary differential equation, this one. In the rectangle D1, we get two ordinary differential equations and four ordinary differential equations with respect to x2. We obtain in the rectangle D sub 2. I would like to pay your attention to the fact that if some parameter alpha sub I is equal to 0, then the corresponding differential equations has zero order terms, since here delta sub I sub alpha I1 is a Kronecker symbol. Now the following questions arises. What transmission condition should be set on the interval I0, I sub 0, I sub 1, and I sub 2 for this function? To answer these questions, we should run the inner asymptotic in a neighborhood of this interval. So in a neighborhood of the joiner zone, we propose the following ansatz for the inner asymptotic expansions. And here you see some coefficients as the capital Z1, capital Z2 that depends on quick variable. They are Junctions layer solutions to some problems in the cell of periodicity P sub 0, that is the union of the semi-strips P plus, this one, and the semi-strip P sub H0 minus, this one. And this cell of periodicity correspond to this joint. In a neighborhood of the first branching zone, capital I sub 1, the ansatz is as follows. And here also you see the coefficients, capital Z1, capital Xi1, and capital Xi2 that depends on quick variables, and they are branch layer solution to some problems, but now the cell of periodicity is different. It is capital P sub 1, which is a union of three semi-strips P sub H0 plus, this one, P sub 1, 1 minus this one, and P sub 1, 2 minus this one. And this cell of periodicity correspond to this branch. And we have two inner asymptotic expansions in the second branching zone, 11 and 12. It turned out that these coefficients that depends on quick variables, they have polynomial growths at infinity. For example, the coefficients capital Xi1 and capital Xi2 should be solutions to the Neumann problems in the cell of periodicity P1. It turns out that there exist two solutions to these problems which have the following differential asymptotics. And you see that these solutions have a polynomial growth at different outlets at infinity. And any other solutions to the homogeneous problems with polynomial growth at infinity can be presented as linear combinations of these solutions. To complete the formal asymptotic constructions and obtain transmission conditions for the coefficients of the outer asymptotic expansions, we have to match the corresponding anti-asymptotic expansions with the inner ones. And the rules is as follows. Here are the rules for the first branching zone. The main term of the asymptotic of each of the expansions as x2 tends to plus minus L1 have to coincide with the corresponding terms of the asymptotic of the inner expansion as psi2 tends to plus minus infinity respectively. So following these rules, we get the transmission condition in the first branching zone. Similarly, we obtain transmission conditions in the joint zone and in the second branching zone. And now we can write down the relations that form the homogenized spectral problems. So in Junctions body, we have the same relations as for the initial spectral problems. In the rectangle D0, D1, and D2, we have respectively 1 ordinary differential equations, 2 and 4. And the following transmission condition on the joint zone, capital I0, on the first branching zone, capital I sub 1, and two kinds of transmission conditions are the second branching zone. And of course, the Neumann boundary conditions for the functions V0 to M. So this is the homogenized spectral problems. I called it CP0. And now here you see that mu0 is a spectral parameter. And also you see from these problems the influence of the constants H sub I M and the parameter alpha sub I. And the functions V sub 0 plus V sub 0 I M form multi-sheeted functions. So the functions V0 plus is defined in the Junctions body. The functions V0 0 is defined in the rectangle D0. Two functions are defined in the rectangle D1, and 4 functions are defined in the rectangle D2. And these functions are connected by transmission conditions in the joint zone, capital I sub 0, capital in the first branching zone, capital I sub 1, and in the second branching zone, capital I sub 2. Next, to shorted formulas, I consider the case when our thick fractal junctions have only one branching zone, and consider the case when parameter alpha I is greater than 1. So we defined the corresponding anisotropic Sobolev space of multi-sheeted functions, the space capital bold H sub 0. The first component phi plus belong to the corresponding Hilbert space in Junctions body, and the next components are from the space L2. They have big variative with respect x2, and they connected with the trace correspondingly in the joint zone and branching zone. The space H0 continuously and densely embedded in the space V0 of multi-sheeted functions whose component belongs to L2, and the scalar product are defined by the following formula. The homogenized spectral problems is equivalent to the spectral problems of the operator A0 acting in the space H0, but now this operator is self-adjoint, positive, continuous, but non-compact. And I show you how we can reduce our problems into the nonlinear spectral problems for the operator functions. So taking into account of the Neumann conditions, we get the following representations for the functions V0, 1m, and the following representations for the functions V0, 0. Here, B, C, and are some constants. Substituting successively these representations in the transmission conditions and on the fast branching zone and in the joint zone, we obtain resulting spectral problems in the junctions body and with the following strange boundary conditions. And here you see that the spectral parameter mu0 occurring both in the differential equations and in the boundary conditions on the joint zone. In the case if the six junctions have two branching zone, the conditions on the I0 is more complicated. It is as follows, and you see that this functions is defined by the following big four formula. And if some parameter alpha is equal to 1, then this conditions is as follow, where the function g is defined by this formula. And here this constants came from the Robin boundary conditions. So if we consider our functions f and calculate its derivative, it is easy to verify that this derivative is positive. And on these slides, you can see the graph of the functions f for different values of L1 and L2. And these graphs remind us the tangents graph. So now we return to the resulting spectral problems, and big formulations of these problems give us the nonlinear spectral problems for the operator functions A. And again, applying my results of my papers, we can state that the spectrum of operator functions L contain a normal eigenvalues and also the left accumulations points Pm that are roots of the transcendental equations, this one. These points of the essential spectrum divided the eigenvalues into the sequences and solve other homogenized spectral problems. Spectrum of the homogenized spectral problems has the following structure. So the next step in our study is to construct the asymptotic approximations for the eigenfunctions. Unfortunately, I have enough time. Yes, Professor Gaudiello, how many minutes?
Over, already over.
So then I show you only some results as main results. So only points of the spectrum of homogenized spectrum problems are accumulations points for the spectrum of the initial spectral problem C P epsilon. Also, we prove law frequency convergence for any fixed n lambda sub n of epsilon converges to the corresponding eigenvalues of the homogenized problems from the first series. In addition, we obtain asymptotic estimates for this convergence, both for eigenvalues and eigenfunctions. And from the Hausdorff convergence of the spectrum, it follows that for any eigenvalues from the other series of the homogenized spectral problems, there exist some sequences, but now here the number n depends of epsilon, such that these sequences converge to these eigenvalues. But now we can state more strong results that if we have some R multiple eigenvalue of homogenized spectral problems, then for any delta, for sufficiently small epsilon, this interval contain exactly R eigenvalue of our initial problems, and some results asymptotic estimate for approximation functions. So thank you for your attention.
Thank you for this interesting talk. Any question? Any remark, comments? Okay.
So,
it seems no question. Thank you.
I see here some remarks. Yes, of course, I can see a copy of these papers. Yes.
Okay. Thank you very much for this talk. And I think we resume in 20 minutes.